This is the overview talk for the parallel session 3 on origin, evolution, and exploration of planetary crusts, and it will be given by Chip Shearer, and he'll be talking about comparison of ancient planetary crusts. Thanks, Chip.
Thank you very much. First, I just wanted to acknowledge my co-authors that are shown here on this for this talk, and actually for the this special session or this session. Just to give you just a little taste of what's coming up the rest of the morning, the themes within the origin, evolution, exploration of planetary crusts is outlined here. We have several talks on chronology of lunar events, led by the first talk by Lars Borg. Then this is followed by a talk that focuses on processes of new crustal formation, primarily focusing on silicic magmatism on the moon. Then a series of talks on the characteristics and structures of planetary crusts, and then follow that up with, the exploration of planetary crusts with two examples of potential lunar missions to better understand events and the crust on the moon, and also a final curation type of talk of what to do once we have those samples in order to extract the most valuable information from them. Again, what I'm going to be focusing on is primarily the primordial crust and primordial differentiation, and this is a diagram that I've modified from diagrams that were produced by Ross Taylor and Jim Head, and just kind of shows the linkage among various stages and the evolution of a planetary body, from accretion to primordial differentiation, through secondary and tertiary crustal formation, to finally robotic and human exploration. And the one link that I'd just like to look at is the link between accretion and primordial differentiation, and that the timing of the accretional event and the duration of it, the characteristics of the material that are accreting to form that planetary body are all important in the eventual primordial differentiation, whether you have a wholesale melting of the body or even just simply metamorphism. And what I'd like to do today is primarily focus upon the diversity that we see in some of these primary crusts, both in small bodies and larger planets, the role of FO2, or the oxygen fugacity in volatiles, and primary crust diversity and crustal evolution, links between or among FO2 volatiles and styles of primordial crust formation, and then throwing out some examples of future research and potential questions that, again, we can link to the parallel session later this morning. This diagram just really shows some of the diversity that one sees in some of these initial melting products produced during the initial stages of differentiation. These are primarily crustal lithologies, and there's a great deal of diversity. For example, in the upper left-hand corner, the angrites, these are very, very exotic lithologies representing exotic melts that appear to be very silica undersaturated. They have olivine, but commonly two types of olivine: iron magnesium olivine, like most of us are familiar with, and basaltic magmas, but also they have calcium substituting in an iron magnesium site, so you have a calcium rich olivine. Also, there are other pyroxenes that have exotic sorts of compositions, like fasciite, for example, or fasciitic pyroxenes. In addition to that fairly exotic sort of crustal lithology that was produced fairly early in the evolution of the solar system, there are other rocks or meteorites such as GRA 06129, 128, and this is shown in this image right in here, which is a BSE, backscatter electron image. And what's quite interesting is the purple color just illustrates that this is dominated by feldspar, and very sodic feldspar, very untypical of most other crustal rocks making up asteroids. And then finally, another one. I'm just trying to show you the general range of compositions. The image just on the bottom, eucrites and diogenites, presumably from 4 Vesta or other differentiated meteorites. And these are more along the lines of basaltic in composition and more traditional basalts. Also shown here are potential primary crusts on other bodies, such as has been proposed from the messenger data, graphite perhaps making up the primary crust or being a component of the primary crust on Mercury. Mars, there are several ancient rocks, such as Allen Hills 84001, which is orthopyroxenite, but also there are some even slightly older rocks that are classed in some of these Martian breccias that are essentially very exotic, that consist of pyroxene, ilmenite, and apatite. That's essentially it. But those are on the order of 4.4 billion years old. And then, of course, as Lars will be discussing during the first talk of the session, we have our fans making up the moon, and he and I actually had a long argument last night in terms of what really is crust. And so what I'm going to do next is really look at the range of FO2s, or the degree of the amount of oxygen in these various systems. And this is reflected in again, the oxygen fugacity. And this shows the wide range of FO2 in a lot of these bodies. The solar nebula and some of the more reducing components that were produced in the solar nebula, crystallized and were produced at iron wustite, -7, -8, highly reducing. You can see here Mercury is again fairly reducing on the order of maybe -4 to -6. The moon and the eucrite parent body on the order of iron wustite -1. The angerites and the GRA 06128 and brashenite parent bodies, that's still debated in terms of the conditions in which those crusts were produced. A number of people think they were produced at fairly oxidizing conditions. The next diagram is a little bit complex. This is a phase diagram, which I'm sure many of you aren't that familiar with, and how to analytically approach these. But I just want to use this diagram to illustrate the impact of just simply FO2 on crustal composition and crustal mineralogy. This is what you see here is a projection on a surface of the system, olivine quartz, halonite, and essentially a calcium nepheline. This is a slice where along this axis here, the laranite is up in this part of the ternary, orthopyroxene is here, the calcium nepheline component is along this line, so we're only looking at a small part of that triangle. What we have here are fields, liquidus fields that are projected on the surface. So if you have a melt composition in here, you're essentially crystallizing out augite plus olivine. If you're in this field, it's plagioclase plus olivine. Along these liquidus reaction boundaries, you essentially, like along this boundary right here, you're crystallizing plagioclase, olivine plus augite, and then you have these individual reaction points here, where multiple phases do crystallize. The point I want to show here is if one takes chondrite compositions that plot along this line right here. Oh, the other point I want to make, which is really important, there is a thermal divide within this system in which melts that are on this side of this dashed line crystallize in this direction, melts that are on this side of that thermal boundary crystallize in this direction. So if we have very reducing chondritic material, some of the iron, or a lot of the iron goes into metals, so that essentially you have iron loss within the silicates, and the bulk compositions plot along in this area right in here. If, however, you have the chondritic material and it's more oxidizing, it tends to plot along this area right here. So if one has reducing chondritic material that you're melting, and in the first episode of differentiation, to form crust, one produces melts in this field, or rocks that are or magmas that are very similar to eucrites. If, however, you're fairly oxidizing in this field here, or this bulk compositions, one produces melts at this composition here and along these reaction lines, which are very, very similar to the angrites. So just simply variations in the FO2 may change the overall bulk composition of the crust that's being produced during primordial differentiation. Now one can look at the impact of FO2 on other volatile elements, and other volatile elements also impacting how they essentially are incorporated in reservoirs and planetary mantles, and how they essentially impact the formation of primordial crust. This is just a diagram from a paper that I put together with Zach Sharp, which just kind of illustrates how the fugacity of H2 changes and the ratio to the fugacity of H2O. And at the QFM buffer, or a fairly oxidizing environment very similar to the Earth, most of the hydrogen species is H2O. However, at a more reducing oxygen fugacity, very similar to the Moon, at iron wistite -1, that ratio is dominated by H2. Very, very important, because both phases, or both species, will impact melting and crystallization significantly. And so this diagram just illustrates some of the differences in this volatile ratio. And again, this is the fugacity of H2O to the ratio here. This again shows that at low FO2s, it's dominated by H2, and until we get into Mars and Earth, those systems are dominated by H2O. Now, what is the overall effect of H2O on, for example, melting of a magma ocean or crystallization of a magma ocean? That's shown in the diagram to your left, which is temperature versus pressure in GPa in gigapascals. And what you'll see is some data from a paper by Alardo, Draper, and myself, that we looked at the crystallization and melting, the crystallization of a lunar magma ocean of the Taylor whole moon composition. And the liquidus, dry liquidus, is shown right here, fairly high temperature. The first phase to crystallize over a wide range of pressures in lunar composition, in lunar pressures, is olivine. And then this is the solidus, shown right here in green, with a variety of different phases crystallizing and stable between the liquidus and the solidus. However, if we add H2O, not H2, one can lower that liquidus with 2.9% water. That's the liquidus temperature here compared to here. This is the solidus. This is the solidus here compared to the solidus here in dry conditions. Again, H2O, if it's stable, will lower the crystallization and change the crystallization temperature, and also change the sequence of crystallizing phases. And again, if one takes this to an extreme, shown in this dashed line right here, this is the water saturated solidus for this lunar magma ocean bulk composition. So water does have an important impact, but again, on the moon, where you're dominated by H2 versus H2O and during differentiation, one perhaps has this sort of relationship rather than this one. The diagram to the right is the impact, and illustrating the impact of sulfur, another volatile element, on crystallization within during initial stages of differentiation. This line right here, again, is a series of chondrite compositions. If one moves up in this direction, this is at low sulfur fugacity. in this direction at high sulfur fugacities. And again, this behaves very, very similar to oxygen fugacity, in that if one has low sulfur fugacities, most of the iron is within the silicates, and therefore one has melting potentially in this area of the phase diagram, where if one has fairly high sulfur fugacity, one will have melting here. And then finally, let's go ahead and take a look at carbon. And this is some work by Van der Kayden and McCubbin, where they essentially examined the potential for a volatile-rich planet, Mercury, which has a high potassium-thorium ratio. The magma ocean potentially crystallized at very, very low FO2. And you see here in this diagram, one has pressure plotted against density, and that in a lunar magma ocean with this sort of density over a wide range of pressures, the graphite, which should be stable at these FO2s and that this volatile-rich system, should float and partially form a crust. This is all of this data, the FO2, the volatiles, and the styles of primordial crustal formation are illustrated here with regards to small bodies, the moon, and Mercury, which may have flotation cumulate primary crust, and again Mars and the Earth, again off to the right-hand side, illustrating the relationships between the style of differentiation, the volatile content, and the FO2. These just list examples of future work and questions that we will be addressing in the future and in the morning session, session 3, ranging from how to improve thermal models for asteroid and lunar melting, what is the chronology of lunar accretion and primary crust formation, and the interactions among all those variables. All these questions really require the integration of substantial sample and experimentally derived data in integration with mission observations and modeling. And again, the survey provides a really great forum where all of us can really interact on all these sets of data and being able to integrate these sets of data. Thanks.
We do have time for a few questions. I see a few heading that way.
Hi, Chip. As you pointed out, the meteorites are really fascinating because they represent maybe 150 small bodies that have incorporated different amounts of volatiles, which led to different petrogenetic results, which can be measured in the samples. But I'm wondering if you can comment a little bit on the role that pressure would have, so large planet versus these small planetesimals, with respect to the influence of volatiles on the differentiation of different sized bodies.
Well, I think if one is looking, for example, the role of water on a small body, particularly if it's a reduced, fairly reducing environment, I think the chances of water having a substantial impact on melting is probably fairly low. However, things like sulfur, I think, may be key. And as you saw in that diagram from John Longy, sulfur, if it's abundant and it removes a substantial iron from the silicate portion of the system, may dramatically impact, what the melt composition is within that system. So that's key, and FO2 is key. Carbon maybe, but I'm not sure. I haven't looked very closely at that. Yeah, Bill.
I just wanted to ask a quick question. You covered a huge amount of ground.
Yeah,
I'm going to bore in on one topic, which is,
sure.
you touched on like 30 seconds. But the issue of mercury and the graphite sort of struck a chord with me because I'm of the suspicion that a lot of that carbon we see is simply implanted by micrometeorites. That would explain the lower albedo. You can get a lot of micrometeorites, and the flux is about an order of magnitude higher than what we get at the moon for Mercury. So
Right.
if that were to be true, how would that change our interpretation of Mercury's history? Just imagine the carbon, so you don't need to worry about the graphite. It's
Okay.
something else. So.
Yeah, again, I really don't know, from the volatile-rich nature of the experiments that McCube and Vanderkamp did, they essentially tried to look at what volatile state and what species carbon was involved in. And so, if you take essentially that model away in terms of flotation of carbon, because all the carbon is implanted, I think one still needs a magma ocean in order to produce cumulates to have these very sulfur-rich surface materials that were erupted, and some of the secondary crust that was produced by basaltic flows. I still think you need a magma ocean.
Yeah. So okay.
Diane Wooden, NASA Ames. I'm very intrigued with the carbon problem, so I wanted to stimulate
Sure.
you to think about that more, mostly because I've spent a couple decades studying comets, both being a follower of the sample return missions analysis and also remote sensing and back to Halley. Basically, those primitive outer icy bodies and the larger ones appear to have a significant amount of carbon. So I've always wondered, where did the carbon go? And Harold Connolly and others have looked at melting. Basically, comets have that very low oxygen fragacity, mineralogy, and a lot of carbon, and possibly just elemental carbon. 25% of the carbon in Halley was just elemental. So one wonders, where did it go? Could it have gone into CO, for instance, if you did have reactions of oxygen with carbon on grain surfaces or in the gas phase? You could put in a reservoir which is unreactable. And just been wondering the importance of carbon in these processes. So I appreciate your talk, and just wondering where did it go? Because you did show this. You show the iron range and the.
What I don't know is the impact of carbon on the melt composition. My guess is, in terms of the melting reaction itself, just the carbon graphite would be inert. However, another model for the angrites, and I show the model that one could produce the angrites at more oxidizing conditions. However, if one has graphite, and people have suggested if one has substantial graphite in the angrite parent body mantle, one may be able to react and produce small amounts of CO to essentially enable production of angrite magmas, these exotic magmas, at fairly reducing conditions like iron westite, rather than more oxidizing conditions. I know I didn't answer your question.
But yeah, well, thank you. This also just came to mind that Rosetta is seeing an incredible number of sulfur-bearing molecules, molecules with, say, 10 or less atoms, but huge amount of sulfur. So the sulfur also plays in. I appreciate that.
Yes. And on GRA 06128129, we're kind of looking at the role that sulfur plays in producing those very exotic melts for meteorites. These are, have plagioclase compositions that are AN15, so they're very sodic, very unusual for primordial crusts at all. You'll find some fragments in other types of meteorites, but again, as I mentioned earlier, sulfur may be the key.
Thank you.
Yep.
Thanks very much.